this is the alternate option of question 12. Here in this question, we have a curve y equals to x times x minus 3 whole squared, which has a maximum point at P and a minimum point at Q. A tangent is drawn at P and a normal is drawn at Q. These two lines meet at point R. We need to find the shaded region enclosed by these two lines and the curve as given in the figure. So let's start. Let's write y equals to x times x minus 3 whole squared. Let's expand x minus 3 whole squared term. So in the next line we can write y equals to x times x squared minus 6x plus 9. Now in the next line we can write y equals to x cubed minus 6x squared plus 9x. Now we need to differentiate y with respect to x, so we can write dy over dx equals to 3x squared minus 12x plus 9. This is the equation to find a gradient on any point of the curve. So at maximum and minimum point, the gradient of the tangent is 0. So dy over dx equals to 0. So using dy over dx equals to 0, we can write 3x squared minus 12x plus 9 equals to 0. Let's divide the entire equation by 3. So in the next line we can write x squared minus 4x plus 3 equals to 0. Now let's solve this equation with the help of middle term factorization. So we can write x squared minus 3x minus x plus 3 equals to 0. If we take x common from the first two terms, we get x times x minus 3. Then let's take common minus 1 from the last two terms. So again we can write minus 1 times x minus 3 equals to 0. Now in the next line, let's take x minus 3 common. That gives us x minus 3 then times x minus 1 equals to 0. Therefore we can say that either x minus 3 equals to 0, which gives us x equals to 3, or we can say x minus 1 equals to 0, which gives us x equals to 1. So these are the x coordinates of the stationary points, hence the turning points, hence the x coordinate of either minimum or maximum points. From the figure we can easily say that the x equals to 1 will be the x coordinate of P and x equals to 3 will be the x coordinate of Q, but let's prove that mathematically. We need to do the second order derivation. So let's differentiate dy over dx with respect to x again. So we can write dy over ddx of dy over dx equals to ddx of 3x squared minus 12x plus 9. So now in the next line, d squared y over dx squared equals to 6x minus 12. So this is our second order derivation. Now we need to substitute the x values of the stationary points in our second order derivation equation. So we can write when x equals to 3, the d squared y over dx squared equals to 6 times 3 minus 12, which is 6. The 6 is greater than 0. When the second order derivation gives a positive result using the x coordinate of the stationary points, at that point the minimum point occurs on the curve. So at x equals to 3 we have minimum point. Now let's use when x equals to 1. So when x equals to 1, our d squared y over dx squared is equals to 6 minus 12, which is negative 6, that is less than 0. So since second order derivation is less than 0 using the x value of stationary point, we can say at x equals to 1 we will have the maximum point. So we can say the x coordinate of P is 1 and x coordinate of Q is 3. Now let's mark some points on the x-axis in the figure. Right below the P it will be 1 0, it will be 1 0, and the coordinate of Q will be 3 0. The x coordinate of R will be 3 as well. So let's write the x coordinate of the R here. We need to find the y coordinate of the R. The y coordinate of the R will be the y coordinate of the P. So at x equals to 3, no, we cannot find in that way. We need to use the x coordinate of P to get the y coordinate of P, because the y coordinate of P will be the y coordinate of R as well. So when x equals to 1, substituting this value in the original equation, we get at P y equals to 1 times 1 minus 3 whole squared, which gives us 4. So the coordinate of P is 1 4. So therefore the coordinate of the R is 3 4. So now finally we have the coordinate of R. Now we need to find the area of the shaded region. So we need to find the area of the shaded region. Area of the shaded region can be defined by area of the rectangle minus the area under the curve y equals to x times x minus 3 whole squared. Here so let's write it first. Area of the shaded region, area of the rectangle minus the area under the curve. Here the area of the rectangle is QR times PR. So we need to find the length of QR. The y coordinate of R is 4 and y coordinate of Q is 0, so QR is 4. Now we need to find the length of P, which is 3 minus 1, that is 2. So area of the rectangle is 4 times 2. Now to get the area under the curve, we need to integrate from 1 to 3 with the limit the curve x cubed minus 6x squared plus 9x dx. So in the next line we can write 4 times 2 will give us 8 minus, if we do the integration, we can write x to the power 4 divided by 4 minus 6 times x cubed divided by 3 plus 9 times x squared divided by 2. Now let's put the limits, that is 1 and 3. We don't need the integral constant here as it is a definite integration. So in the next line we can write x minus, now putting the upper value, that is upper limit value, that is 3. So we can write 3 to the power 4 divided by 4, then minus 2 times 3 to the power 3 plus 9 times 3 squared divided by 2. Now let's use the lower limit, that is 1. So we can write 1 by 4 minus 2 times 1 plus 9 by 2. So now let's use the calculator. We can get that value will be, I'm using the calculator, so our value will be 4. So the area of the shaded region will be 8 minus 4, that is 4 units squared. So the entire paper is done. So we will solve another paper next time. Goodbye.